Search a 2D matrix. If you can spot hidden structure, you win interviews. Search a 2D matrix disguises a sorted array inside a grid and tests whether you can binary search it without flattening anything in memory. This Pattern Mastery 100 Classic Filters for Pointer Precision and Index Math. Let's solve it with basics so you can explain it cleanly and code it fast in O of log of m times n. Breakdown. We're given an m by n matrix where each row is sorted in ascending order. The first element of each row is greater than the last element of the previous row. That structure means the matrix behaves exactly like one long sorted array of length m times n when read row by row. Given a target, we return true if it exists and false otherwise. Assess. A naive scan is O of m times n, but because the matrix is globally sorted, we can run a standard binary search in O of log of m times n with O of 1 extra space. The key trick is mapping between dimensions. Row equals mid divided by n, using integer division. Col equals mid modulo n. Or using Python's built-in row col equals dov mod mid n. Structure. The plan is straightforward. Guard against empty inputs. Set left to 0 and right to m times n minus 1, while left is less than or equal to right. Compute mid. Convert mid into row and column. Compare matrix at row and column to the target. If it matches, return true. If the midpoint value is smaller, move left to mid plus 1. Otherwise, move right to mid minus 1. If the loop ends with no match, return false.
Let's try to implement it using solution 1. We begin by defining the solution class, which will hold the method we're explaining. Then we declare the search matrix method, which receives a two-dimensional matrix and the target value we want to look for. Next, we check an edge case. If the matrix has no rows, or the first row has no columns, there is nothing to search, so we immediately return false. After that, we store the number of rows as m, and the number of columns as n. These help us convert between a one-dimensional index and a two-dimensional row and column during binary search. Now we set up binary search boundaries over the flattened matrix. L starts at 0. R starts at the last virtual index, which is m times n minus 1. This lets us treat the entire matrix as if it were one sorted array. Next, we begin the binary search loop. Since each step halves the search space, this runs in O of log of m times n. Inside the loop, we compute the midpoint index. This tells us which virtual position in the flattened matrix we are checking. Here is the clever part. We convert that one-dimensional midpoint into a two-dimensional position. Mid divided by n gives the row. Mid modulo n gives the column. Then we read the value stored at that row and column. If that value matches the target, we immediately return true. That means we found it. Otherwise, if the midpoint value is smaller than the target, we move the left pointer to mid plus 1. That is because the target must be in a higher section of the virtual array. And if the midpoint value is larger than the target, we move the right pointer to mid minus 1. That is because we need to search the lower section. This continues until the loop ends. By then, we have either found the value or eliminated the entire search space. And finally, if the loop finishes without a match, we return false. That means the target does not exist in the matrix. And that's how this algorithm works. It first checks that the matrix is valid. Then it treats the entire grid as a single sorted list and uses binary search. At each step, it converts one-dimensional indices back into two-dimensional positions to compare values. Efficient, simple, and elegant. Check. This test verifies the matrix search algorithm for the search a 2D matrix problem. The matrix contains 3 rows. Row 1 is 1, 3, 5, 7. Row 2 is 10, 11, 16, 20. Row 3 is 23, 30, 34, 60. The target value is 3. The matrix satisfies the required properties. Each row is sorted, and the first value of each row is greater than the last value of the previous row. So the whole matrix can be treated like one flattened sorted array. To locate the target, we can reason about where it would appear. 3 lies between 1 and 7, so it must be in the first row. Within that first row, the value 3 appears in the second position. So the algorithm correctly concludes that the target exists in the matrix. It returns true. The output is true, matching the expected true. This confirms the matrix search correctly identifies the presence of the target value. Now let's try another implement approach using solution 2. We begin by defining the solution class. This is the container for our method. Then we declare the search matrix method. It receives a two-dimensional matrix and the target value we want to locate. Next, we handle an edge case. If the matrix has no rows, or the first row has no columns, there is nothing to search. So we return false immediately. After that, we store the number of rows as m and the number of columns as n. This makes the rest of the logic easier to follow. Then we set up three variables for the first phase. Top starts at the first row, bottom starts at the last row, and row starts at -1, meaning we have not identified a valid row yet. Now we begin our first binary search. This search runs across the rows of the matrix. We compute the middle row and check whether the target could belong to that row. If the target is smaller than the first value of the middle row, it must be in a row above, so we move the bottom boundary up. Otherwise, if the target is larger than the last value of the middle row, it must be in a row below, so we move the top boundary down. If neither of those is true, then the target falls within the value range of that row, so we store that row index and stop the raw search. After the loop, if row is still -1, then no row can contain the target, so we return false. Now we begin the second phase. We run a standard binary search inside the selected row. We set L to the first column index, and R to the last column index. We continue as long as the left pointer has not passed the right pointer. We compute the midpoint within that row. If the midpoint value equals the target, we return true immediately. If the midpoint value is less than the target, we move the left pointer to the right. Otherwise, the midpoint value is greater than the target, so we move the right pointer to the left. If this inner search ends without finding a match, then the target is not in the matrix, so we return false. And that's how this algorithm works. It first uses binary search to identify which row could contain the target. Then it uses a second binary search within that row to locate the value. This cuts the search space down efficiently at both stages. Efficient, simple, and elegant. Check. This test checks the behavior when the target is not present. The matrix has 3 rows. Row 1 is 1, 3, 5, 7. Row 2 is 10, 11, 16, 20. Row 3 is 23, 30, 34, 60. The target value is 13. The matrix structure allows binary search because each row is sorted, and each row begins with a value greater than the last value of the previous row. Now consider the target 13. It is greater than every value in the first row. In the second row, it falls between 11 and 16, but it does not match any value in that row, and it is smaller than every value in the third row. So no row contains the value 13. A full search would conclude there is no match. Therefore, the correct output is false. The output is false, matching the expected false. This confirms the solution correctly identifies that the target does not exist in the matrix.
Let's have a quick recap. Breakdown recap. So, wrapping up, search a 2D matrix is all about recognizing structure. You're given a matrix where each row is sorted, and every next row starts higher than the last one. Conceptually, that means the entire matrix behaves like one long sorted array. The challenge is to find the target efficiently, without actually flattening the data. Assess recap. We looked at our options. A brute force scan checks every element in O of m times n, but that's wasteful. Because the matrix is globally sorted, we can treat it as a single sorted list and use binary search. That drops the time down to O of log of m times n, while keeping space constant. The key was mapping a 1D index back to 2D coordinates using simple math. Structure recap. The logic was straightforward. Set up 2 pointers, left at 0 and right at m times n minus 1, and repeatedly check the middle index. Convert that index into a row and column, compare the value to the target, and adjust boundaries until you find it or the range collapses. Implement recap. During implementation, we guarded against empty input, then built a clean binary search loop. Each step calculated mid, mapped it to row and column, and compared the value. The solution stayed compact, efficient, and easy to follow. Check recap. When we ran through multiple test cases, every result matched perfectly. The function correctly returned true for existing values and false for values that were missing. All outputs confirmed the O of log of m times n performance and flawless index mapping.